Okay, so here's the problem that we ended up with last class, right at the end. So we'll do this one as a refresher. All right, so it says, what is the heat capacity of a container if 100 grams of water at 100 degrees Celsius are added to the 100 grams of water at 25 degrees Celsius in the container, and the final temperature is 61 degrees Celsius. All right, so we have two containers of water, one at 100 degrees Celsius. All right, and then another one at 25 degrees Celsius, correct? 25 degrees Celsius. And the result, when we add those two together into a third container, or I guess this is the resulting container that contains them both. But we'll just draw it here. It ends up being 61 degrees Celsius. Okay? So we want to know the heat capacity of the container. And essentially what we're saying is, how much energy does it take? How much energy is that container kind of absorbing in the process? Okay, so if I have the 100 grams of water, here the change in temperature for this water goes from 61, no, from 100 to 61. So change in temperature again is temperature final minus temperature initial. So that's final 61 minus 100. All right, 71, 81, 91, 91, 92, 93, 94, 95, 96, 97, 98, 900. 91, so it's 9 more, right? 91. So that's 39 degrees. So the change in temperature is 39 degrees Celsius. All right, that's for this body of water right here. And from that, I can determine how much energy was released by the hot water, right? So I can say 39 degrees Celsius was the change in temperature. How much heat energy was released? Well, if 39 degrees is how much heat energy, or how much the temperature change was, the heat energy that's released is related to the mass of the material that released that energy, the specific heat, which is the joules of energy for every gram degree Celsius, and then that is supposed to be multiplied by the change in temperature. So 39 degrees Celsius was the change in temperature. The specific heat of this stuff, it's water, so it's 4.184, and that's units of joules per gram degree Celsius. And my mass of water, what was my mass of water? It says it was 100 grams of water, 100 grams here. Okay, so from this I can identify how much water was, how much heat was lost by the water. Okay, so I have my 61 times, or minus the 100, right, times 100 times 4.18, and that gave me negative 1.63 times 10 to the 4th joules. That's how much energy the hot water lost. Now, how much energy did the cold water gain? All right, well, it went from 25 degrees Celsius up to 61. So temperature final, 61, temperature initial, 25. So I can put in there my temperature initial, temperature final, 61 minus 25. That's the change in temperature. Again, the cold water was 100 grams of water, and its specific heat was 4.18 joules for every gram degree Celsius. So that'll tell me how much energy was gained by the water. So from this, I can identify the energy gained by the water, and I can compare that to the energy lost by the hot water. So there's a difference. The hot water lost 1.63 times 10 to the 4th joules, and the cold water gained 1.5 times 10 to the 4th joule. 10 to the 4th joules. Did I say 10 to the 4th for the first one? Anyways, there's a difference. Where did that extra energy go? Well, that extra energy went into heating the containers and the surroundings of this system. Okay, so I can take the difference of those energies, and that will be the energy, 1.3 times 10 to the 3rd joules. That'll be the energy that the system kind of consumed in the process of this mixture of two solutions. So the 1.3 times 10 to the third, that's the joules. And I'm looking for C, heat capacity. Heat capacity has units of joules per degree Celsius. Now I have the joules of energy that the system gained. Now I have to just look at the change in temperature that the system underwent. And the system went from the 25 to the 61, right? So it's the same as the previous one. And I can take the heat in joules of energy that the system absorbed from the process, and I can divide that by the change in temperature. All right, so that gives me the the heat capacity of the system, and that's what where our answer came from, right back here, about 35 joules per degree Celsius. All right, I guess it should have been 36, right? If this was 36 joules per degree Celsius. All right. So, a little reminder. Chemical energy comes from the chemical bonds, right? Certain chemicals have extra energy because of their bonds, right? We talked about how gasoline has a lot of energy compared to water, all right? And it also is indicative, it teaches us about the strength of the bonds. Gasoline, the energy in those bonds is, well, there's energy stored in those bonds. Those bonds aren't very strong. They're not stabilizing for the compound. Not like water. Water, the energy in an oxygen-hydrogen bond in water is it's very stable. Those bonds are very strong. All right. And so, when you have chemical reactions, it involves not just the breaking of bonds, but also the making of chemical bonds. So, when we form bonds, that releases energy, and when we break bonds, that requires energy. And that's always the case. Now, sometimes in biology classes, you'll hear the phrase, the reason why ATP releases energy is because it breaks the high-energy phosphate bond. Well, that's kind of a misstatement, because never does it release energy to break a bond. Okay, it always requires energy to break a bond. The release in energy only comes from forming a bond. The ATP process that they always are describing, they never talk about the resulting bond that is formed after ATP's bond is broken. After ATP, the bond is broken and you result in ADP and a phosphate. That phosphate that leaves goes and forms a more stable bond than it was with in the ATP molecule. And the result is a release in energy. So always when bonds are formed, do you lose energy, and when bonds are broken, it requires energy. Okay? Exothermic reactions. Exothermic reactions, I think you guys have probably heard this before, but they're reactions that release heat as the process proceeds. The example here at the bottom, we have methane gas combining with oxygen gas to form carbon dioxide and water. This is very similar to the octane burning with oxygen. The process is very exothermic. And we can write in heat, if we want to, as a product, right? Because it means that heat is being given off by this process. Endothermic reactions, same thing. They require energy. Sometimes it's heat energy. Sometimes it can be light energy. Photosynthesis is an example of an endothermic reaction that requires energy to proceed. So we can include that energy as reactants. So in exothermic processes, the heat or energy acts like a product, and in endothermic reactions, heat or energy acts as a reactant. All right, bond strength. The stronger the bond, right, the harder it is to break, and therefore the more stable the compound. If a strong bond is broken, it requires a lot of energy. And if the resulting product has weaker bonds, then that means the new products are not as stable, right? So if you have let's do a quick example here. If I have a process here where B reacts with CD to form new compounds, we'll say it's AD and CB, all right? If this process occurs, and the bond strength between A and D and C and B is weaker than the bond strength here, then it's going to require energy to go into this. So we're going to have energy on this side if the resulting bond strengths are weaker. If the new bond strengths are stronger, then that will release energy because these were weaker bonds and now we're forming stronger bonds. So then we'll have energy as a product. All right. So again, how the energy is required to go in or whether we get energy out, that's based on the relative comparison of the bond strengths of the products to the bond strengths of the reactants. All right. So fuels, something can be regarded as a fuel because it releases energy after it reacts, right? So here's our example of methane reacting with oxygen. The products are much more stable. The bonds are much more stronger than the reactant bonds. All right, the product bonds are much stronger than the reactant bonds. Therefore, this is going to be an exothermic reaction, releasing energy. All right, the heat of reaction is a term for how much energy is either required or released as the reaction occurs. Okay, so, and that's one of the main things that we want to get out of this chapter, the second half of this chapter here. We want to recognize that when I write a chemical reaction like this, just some general chemical reaction, AB going to C, all right, I can say in this reaction, maybe I'll put some numbers in here to make it a little more interesting. I can translate this into English. 1 mole of A plus 2 moles of B reacts to form, scoot this over a little bit, 3 moles of C, right? We know that translation. We're familiar with that. And now I can add a little bit to it. By putting some information about the energy, I can say 1 mole of A plus 2 moles of B reacts to form 3 moles of C and releases a certain amount of energy. All right, because I say and releases because the energy is a product here. Okay, if the energy was over here, then I would say something along the lines of 1 mole of A plus 2 moles of B requires energy to react to form 3 moles of C. Okay, so we can put that energy on there, and I'll show you exactly how we'll include it. But for now, this is something that we want to be familiar with, the fact that energy can act as a reactant or a product, and we want to be able to state that appropriately. All right, so heats of reaction. Usually we measure heat of reaction under one of two kinds of conditions. Either constant volume, all right, constant volume meaning we're not allowing the system to expand. If gas is produced, it's contained in the container. Or constant pressure, and this is an open system, a system that's open to the atmosphere. The pressure of the atmosphere is constant, and the reaction occurs, but it's still open to the atmosphere. And usually we're talking about heats of reactions when we're just, we have a container on the bench top in the lab somewhere. It's open to the atmosphere. That's usually the open or the kind of chemical reaction we're talking about. So we have to have a little conversation about pressure, because pressure is how chemical reactions release some of their energy. Sometimes after a chemical process, the number of moles of gas that are in the products is more than the moles of gas in the reactants. For example, if I have a chemical reaction here where A, which is a solid, combines with B, which is a liquid, and the product is C, and all of a sudden C is gaseous, gases take up a significantly larger volume than do solids or liquids. So then all of a sudden you have an explosion, a chemical reaction where you mix a solid and a liquid and it makes a lot of gas. Or another way of looking at it is there's more moles of gas on the product side than the reactant side. That's an example of an explosive reaction, a reaction that produces a lot of pressure and also a reaction that does a lot of work. All right, so pressure is when gas is a product, and pressure is the force that's created by that gas that's produced, and it has to do also with what area that force is exerted in. All right, so the pressure that is produced because products are gaseous results in work that a reaction can perform. All right, so let's see here. Work, the way that we define work is by uh, the amount of volume that the system changes, how the volume changes, because that's gas that's produced. Gas that's produced, right, results in the change in volume. And you can have a condensation reaction, reactions where you start off with maybe uh, some chemicals that are gaseous. For like example, A and B could be gaseous here, and the resulting product could be a solid, some sort of reaction like this. And in this case, the result would be a smaller volume in the product form. And so this reaction would benefit from the atmosphere compressing these two chemicals together to form a solid. Okay? So you could actually get work done by the surroundings on the system in some cases. All right? So the change in volume is going to relate to us how much work was either done on the system or by the system. Okay. Now, the work that actually is produced by the system or on the system is also dependent on what the pressure is, the surrounding pressure. Because if, for example, you start with reactants that are not gaseous and you end with products that are gaseous, then the volume that is created, the space that's created, has to push the atmosphere out of the way, right? So we've had this discussion before where we imagine ourselves on the Earth, standing on the surface, but really we're at the bottom of an atmosphere of oxygen, right? And if we want to have a chemical reaction occur here on our tabletop here, there's the chemical reaction. It's just some solid, but then it's going to produce a gas that's going to take up that much volume. It's going to make the surface of this ocean that we're at the bottom of the atmosphere, it's going to make it rise up, and that's going to require a little bit of energy. All right. So when work is done, the change of volume occurs. How much work is done is dependent on the pressure that was surrounding the system. Okay. So work equals negative sign, and now the negative sign is there to keep our convention the same, because it used to, and negative sign means that the work is released, therefore we want the resulting energy due to the reaction to be negative, to show that it released that much energy. So we put in that negative sign there. Work equals negative pressure times the change in volume. All right. So we can calculate the associated work with the expansion of a gas from 152 to 189 liters at a constant pressure of 17 atmospheres. Okay, so work is the change in pressure the change in volume times whatever the pressure is, and we want to give that a negative sign for our convention. Okay, so the pressure here is 17 atmospheres and ATM, atmospheres, and the change in volume is final minus initial, 189 liters, gas from 152 to 189, 189 minus 152, right? So final volume, 189 minus initial volume, 152. That's our change in liters. What is that? 152, 62, 72, 82. Let's see, 189, 37. So that's 37, and that's a positive value, 37 liters. So 17 times 37, and I'm putting the negative sign in there by convention, and that's consistent with what we expect because the gas expanded going from 152 to 189. So let's see, 17 times 37 up there. I think that should be about 629, right? Now it looks like A and B are both 629. So how do we know if it's positive 629 or negative 629? Well, we got a negative here, but we want to make sure we did it right. make sure we didn't just confuse ourselves. Let's double check this. It says we want to know what the work is associated with the expansion of a gas. So the gas had to expand from 152 to 189. And in doing that, it was hard for the gas. The gas had to push the atmosphere out of the way. There was 17 atmospheres worth of pressure. It had to push those 17 atmospheres and make space for it. So that would make sense that it's losing energy. So a negative 629 would be our value. Okay? So, excellent. Okay, a chemical reaction takes place in a 6-liter cylindrical enclosure fitted with a piston. Over the course of the reaction, the system underwent a volume change from 0.4 liters to 3.2 liters. All right? Which statement below is true? Work was performed on the system. Work was performed by the system. The internal energy of the system increased. The internal energy of the system decreased. The internal energy of the system remained unchanged. So, was work performed on the system or was work performed by the system? Well, if the volume change went from 0.4 to 3.2, that means the work was performed by the system, right? The system did the work and made the piston go up. All right? The internal energy of the system doesn't change, and the internal energy of the system remained unchanged. Let's see. So the best answer here would be RB. Okay. The first law of thermodynamics talks about the change in energy, right? The change in internal energy is constant, right? Energy final minus energy initial, essentially saying that you cannot create or destroy energy. And that's the first law of thermodynamics. Your change in energy will always be zero if you have a perspective throughout the whole universe. Now, your system can change in energy, right? But the system is either losing or gaining energy to or from the surroundings, okay? So, because E is a state function, energy is a state function, we can measure the energy before and afterwards and see how the energy has changed. And that energy change will be due to the change in heat or the change in work. All right? So we introduced heat before in the term, we calculated a lot of problems with heat before, with heat capacity, specific heat, change in temperature. We could identify the heat using those different values. And now we have the ability to identify the work with looking at the change in volume of a reaction at given pressures. Okay, so energy is transferred as heat or work, but you never lose or gain energy overall, right? You cannot create or destroy energy. All right, if we monitored the heat transfer, the heat would always be going somewhere, right? In the form of either heat or work. Okay, so again, a little reminder of our signs, our positive and negative signs for this. If Q is positive, that means heat was absorbed by the system. If Q is negative, that means heat is released by the system. Work is positive, work is done on the system. Work is negative, work is done by the system. And that makes sense because if we think to ourselves, if I have what's called an energy diagram, where I make a y-axis of energy here. Here's my y-axis of energy. And here's my reactants, A plus B. And I'm going to have them react. And then after they react, my new products, maybe it's AB combined here, my new product, if it's lower in energy on this energy diagram, I want to make sure that this here represents a loss of energy that was lost by the system, by the process. All right, so this has to be a negative value. All right, so if we take whatever energy this is, let's say this is at 2 and this is at 4, then final minus initial 2 minus 4 can be excuse me, a -2. So again, the negative sign is an indication that it has lost energy. All right, in either form, heat or work, the negative sign means that the system lost energy. Okay, and a reminder, endothermic, positive values, exothermic, negative values, right? Now, this could happen a variety of different ways. For example, if I have a fully charged battery and I have it connected to a fan, the fan could run for a long time, and that energy could be released in the form of work. A little bit of heat would be lost in the wires as the electrons pass through it, but the majority of the energy could be released in the form of work. But if I drop a wrench across the two poles of the battery, the wrench will melt, right? And all the energy will be released really quickly in the form of heat. But the same amount of energy will be released. All right, so if I have some sort of a chemical reaction and this gas releases 3 joules of heat, but in the process performs 12.2 joules of work, what's the change in internal energy of the gas? Well, the internal energy of the gas, right, it released 3 joules of heat. That is a negative value, -3 joules. And it did 12.2 joules of work. So that's also a -12.2 because the process did that work. So I can combine these two values together, the -3 and the -12.2. And the result is going to be how much energy was changed by this process. What the change in energy was, -15.2. Okay, because the heat was released by the process and the work was done by the process. Okay, so which one of the following is not an expression for the first law of thermodynamics? Well, the first law of thermodynamics says that energy is conserved. It's neither created nor destroyed. It says that the energy of the universe is constant. It can be converted from work to heat, but it's always constant. But E, the energy of the universe is increasing. No, that's not consistent with the first law of thermodynamics. All right, so here we have a chemical reaction that contracts by 1.534 liters under a constant pressure of 2.134 atmospheres. Now, this is the first scenario where we talk about a chemical reaction that is actually contracting, right? Contracting means the volume is decreasing, becoming smaller through the process. So the work energy is related to whatever the pressure is, and they tell us that the pressure is 2.134 atmospheres times, now work was pressure times change in volume. Here, I'll scoot this over. This is our pressure times change in volume. And what is the change in volume? Well, it told us it contracted by 1.534 liters. 1.534 liters. All right. So we can find out our work in liter atmospheres. I forgot to put in here my negative sign, right? Work in liter atmospheres. Now, it said it contracted by 1.534 liters. So it didn't say the initial and the final change, all right? It just said it contracted by 1.534. But if I were to think about that, I'd have to remember that that means that this is a negative value, right? The final, right, was final minus initial, which is change in volume. The final volume was smaller than the initial volume. And so the result is going to be a negative 1.534. And that is consistent with what this work is going to be done, because this work has to be a positive value if it says that the reaction contracted. That means the surroundings did the work on the reaction. All right? And it released 207 joules of heat to the surrounding. So the work is a positive value, whatever this is, value positive, but the energy released to the surroundings was 207 joules. Now we also get the last sentence here that 1 liter atmosphere is equivalent to 101.3 joules of energy. So whatever my answer is here, well, whatever my answer is here, 1.534 times 2.134 atmospheres. Let me get out my calculator, we'll solve this. All right, so we can see that, let's see, where were we at? Okay, so here's how we calculate the work. All right, we have our 2.134 atmospheres, because work is the pressure times the change in volume. The change in volume was 1.534, and that's a result of 3.274 liter atmospheres. Now, they forgot to put the negative sign in front of the negative 1.534. I forgot to put that in there. So what we have here is a positive 3.274 liter atmospheres. And that's consistent because it says that the reaction contracts by that much. So again, it says that for every 1 liter atmosphere, it requires or produces 101.3 joules. So I can take that 3.274 multiply it by 101.3 joules for every liter atmosphere, and it'll tell me how many joules this process consumed by contracting 1.534 liters at the 2.134 atmospheres. All right, so that required, the reaction received 331.7 joules worth of energy. Now it released a total of 207 joules of heat to the surrounding. So I can take that 207 joules of heat and put a negative sign in front of it because that was releasing to the surroundings, add that to the 331, and the result is a change in a positive 131.0 joules of energy. So was this reaction endothermic or exothermic? Well, think about that for a while. You can push pause, talk to your neighbor if you've got one, and see what they say. But the process has to have been endothermic altogether because 131.0 has a positive value on it, meaning that the energy, the total change in energy, was absorbed by the process. All right, now we're going to introduce you to calorimeters. Calorimeters are instrumentation, pieces of equipment that can measure the change in temperature and change in pressure of chemical reactants, right? And this is all done under constant pressure. Well, the pressure, constant volume. Sorry, the volume does not change. And so in the bomb there, they call it the bomb, we put inside a little bit of chemical reactant. We have some way to light it electrically and make the reaction occur, and then after the process occurs, all the energy that's released has to be converted to heat because the volume can't change. So if there is any work volume or work energy that's released or done, then that work energy has to be released in the form, or it has to be converted to heat in the form of pressure, and that will heat up the surroundings, and the surroundings is a large water bath, and all of that energy can be determined change in temperature by the change in temperature. All right, so that's what a calorimeter is. So when we have a chemical reaction like this, where we take a gram of olive oil and burn it in a bomb calorimeter, we see the temperature of the water bath increasing from 22 to 26.049 degrees Celsius, and from this we can determine how many calories are in a gram of olive oil. The heat capacity of the calorimeter in this case is 9.032 kilojoules for every change in degrees Celsius. All right, so I can take the change in temperature, 26.049, temperature final, minus the initial, 22.0. That'll be my change in temperature, 4.049. I can, now, hopefully you remember how you can identify how much heat was released. All right, and if you can't, you can use the units to help you recognize what needs to be done. Okay, so for example, if I now have just recognized that I have 4.049 degrees Celsius, and it's asking me, what is it asking me? How many calories? It's asking for energy. It wants to know how many joules, right? And it also told me something about 9.032 kilojoules per degree Celsius. All right, I might not know what to do with these. I know I'm looking for joules, and I have units here of kilojoules per degree Celsius, and I have units of degrees Celsius here. Well, if I multiply this times units of degrees Celsius, the degrees Celsius will cancel out, and I'll be left with kilojoules, right? So that's another way you can kind of 4.049. I can kind of remind myself what needs to be done because I know I'm interested in energy. All right, so I'm going to take the 9.032 kilojoules per degree Celsius, multiply it by the 4.049, and that's, again, our heat capacity times our change in temperature, and that's how much energy was absorbed by the calorimeter. Therefore, that's also how much energy must have been lost by the oil as it was exploded or burned in this calorimeter. So that 1 gram of oil released the 36.57 kilojoules of energy. You see how we changed the sign, right? Because it was 36.57 joules of energy that the calorimeter had absorbed, positive number, but it's 36.57 kilojoules of energy that the olive oil released, negative number, right? All right. Then I can take that amount of energy, put it over the 1 gram, because that's how much energy it released, 36.57 kilojoules per gram of olive oil. And then I convert those kilojoules of energy into kilocalories of energy, or calorie with a big C. Remember, nutritional calorie is actually 1,000 chemical calories, right? All right, so from this, I can identify that might be off the screen for you, but it's negative 8.740 calories, big C calories, nutritional calories per gram of oil. So make sure you can get that in your calculator, negative 8.740. All right, so if we go to part B of this problem, this chemical, olive oil, is essentially made up of glyceryl trioleate. All right, and there's the chemical formula, C57H1O4O6. And the equation for this chemical combustion is that chemical as a liquid combined with 80 oxygen molecules and produces 57 moles of carbon dioxide and 52 moles of water. And we want to know what the change in energy for the combustion of 1 mole of this stuff is. Well, if we know that we released, let's go back a slide, we released a total of 8.740 calories. Let's see, is it asking us in, it's probably not going to ask us in calories, it's going to ask us in kilojoules. So let's use the 36.57 kilojoules of energy for every gram of oil. And we can convert that gram of oil into moles of the oil, right? So essentially what they're asking is, what's the combustion for 1 mole of this stuff? So it's 36.57 if you have a gram, but we don't have a gram. We have a fraction of, for every gram, and they want to know how much it is for a mole. We don't have a mole, we just have a fraction of a mole, right? So we can convert these grams to moles and to find out how much energy is released for every mole of this oil. All right? So sometimes they'll ask you for the energy per gram of stuff, but usually it's in terms of moles of material. All right. So here's one that you can work on yourself for a while. So I'll let you push pause right now, and I'll let you work on this for as long as you can, and then you can start it up when you're done. Okay, so hopefully you had a chance to work on it. If you didn't, I strongly encourage you to take a chance to do your best to see how far you can get, and then you can watch. But the bomb calorimeter has a heat capacity of 2.47 kilojoules per degree Kelvin in this reaction here, in this problem here that we're presented. And when a 3.74 times 10 to the third mole sample of this chemical ethylene was burned in this calorimeter, the temperature increased by 2.14 Kelvin. So now we want to calculate the energy of the combustion of 1 mole of this of this ethylene. Well, 2.47 kilojoules for every degree Kelvin, and it was 2.14 Kelvin. So we're going to take our 2.47 and multiply it by our 2.14. 2.47 multiply it by our 2.14, right? And that will tell us how many kilojoules of energy was released by this process. Now, this wasn't a whole mole of the stuff. It was only 3.74 times 10 to the minus third mole. So if we take that value over 5.286 kilojoules and put it over the 3.74 times 10 to the minus 3 moles, it'll tell us how much energy was released. Okay? Now, in this blue equation here where it says 2.47 kilojoules for every degree Kelvin, and we multiplied it by 2.14 Kelvin, the 2.14 Kelvin should be a negative number, right? Because that was, it says the temperature increased. So the final temperature was 2.4 higher. Let's see, final temperature, final minus initial. Let's see, is that right? 2.14. Yeah, the final temperature was higher than the initial temperature. Initial, final minus initial. I'm going crazy. What's going on here? Final minus initial. Final temperature was higher. Final minus initial. Change in temperature. Final minus initial. Hold on just a second. What am I? Okay, so the change in temperature of the calorimeter, it went up by a positive 1.4 degrees, or 2.14 degree Kelvin, right? 2.14 Kelvin. And that means that energy was absorbed by the calorimeter. It also means that that's how much energy, 5.286 kilojoules of energy, was released by the process. Now that's how much energy that was released, not by a whole mole, only by 3.74 times 10 to the minus 3 moles. So if we want to know the energy of combustion, if we had 1 whole mole, we have to take the 5.286 and divide it by 3.74 times 10 to the minus 3 moles, right? Because that's how many moles we have. And then our units will be kilojoules for every mole. All right? And so that's going to be about 1,410 kilojoules for every mole. And again, that's a negative sign because the ethylene releases that energy. All right. So I'm going to introduce to you now a new variable, a new term called enthalpy. And enthalpy is essentially the heat energy component of the change in energy. All right. So we've talked about how energy is released as either heat or work, and the enthalpy of the reaction is the term for the amount of heat that is released in a reaction. All right. And we'll often see this in this form. You'll have a chemical reaction of some sort, and then there will be after this something about the change in heat energy, maybe 400 joules, something like that. Delta H equals 400 joules. So what this means is a mole of A combines with a mole of B to form a mole of AB, and because this is a positive sign here, this means, the way you translate that into English, and requires 400 joules of energy for this process to occur. Okay, so that's what and this is our enthalpy term associated with this chemical reaction. So let me write this down, a different kind of reaction here. Let's say we have C plus D going to CD, and the delta H, the enthalpy information associated with this reaction, is a negative 200 kilojoules of energy. All right, what this means is, let me translate this into English. 1 mole of C reacts with a mole of D to produce 1 mole of CD, the negative sign means, and releases 200 kilojoules of energy. All right, so the negative sign here means that the energy is, or the heat energy is a product, and the positive sign here means that the heat energy is a reactant. Requires 400 joules in this case of energy. All right, so that's what we call our enthalpy. All right, so yes, as we described, this is the delta H component for the reactions. Okay, and you can identify the delta H for the reaction if you know the heat energy associated with forming these chemicals, and compare it, or the products, and compare it to the heat energy of the reactants. All right. If the delta H is a positive value, again, this is indication that we have an endothermic reaction. And if the delta H is a negative value, down here, that's indication that it's a energy releasing, heat energy releasing reaction. So it loses it to the surroundings. Okie dokie. All right. A coffee cup calorimeter is a reaction. All right. So we have our coffee cup calorimeter. Coffee cup calorimeter. It's nice and easy. It's just a little container where we perform a chemical reaction, and inside that chemical reaction, temperature is released or absorbed, and the change in temperature, heat is released or absorbed, and the change of temperature tells us how much energy was released. So again, the Q, our heat, can be determined by looking at the change in temperature and multiplying it by the heat, the calorimeter constant, what's called the heat capacity of the coffee cup. So here's an example. We have sodium hydroxide and hydrochloric acid, and we mix them together. And when you mix 50 milliliters of the 1 molar hydrochloric acid and 50 milliliters of the 1 molar sodium hydroxide at initially 25.5 degrees Celsius, the final temperature goes up to 32.2 degrees Celsius. So what is the change in the delta H, change in heat energy, in kilojoules per mole of HCl? Assume for these solutions that our S, our heat, specific heat, S is 4.184 joules for every gram that changes 1 degree Celsius, and that the density of the 1 molar HCl is 1.02 grams for every milliliter and 1.04 grams for every milliliter for the sodium hydroxide. All right, so let's see, this guy looks like he is done. All right, so we're going to look at a few of the different facts about this scenario here. First of all, we would like to find out how many grams of our solution we have, so we can find out how many grams of HCl there are. 50 milliliters, and it's 1.02 grams for every milliliter. That's the density. So we have 51 grams of HCl, and we have 52 grams of our sodium hydroxide, right? We get these by multiplying the volume of the solutions by the density, right? And we also would like to identify, well, the mass total, 103 grams altogether. We also would like to find the change in temperature of the total solution, right? It went from 25.5 to final 32.2. So we take final minus initial, and the changes in temperature is 6.7 degrees Celsius by the calorimeter went up 6.7 degrees Celsius, right? So 103 grams of solution went up by 6.7 degrees Celsius, and the specific heat is 4.184 joules for every gram that you have that change in temperature. So the result is 2.9 times 10 to the third joules of energy released by this process. Now, we were asked, what is the delta H in kilojoules per mole of HCl? So we know how many kilojoules of energy was released by this process, but how many moles of HCl reacted? Well, if we go back here, we see that the HCl solution, it was 50 milliliters of a 0.1 molar HCl. 50 milliliters of 0.1 molar HCl, that'll tell us, and we can use that information this way to identify how many moles of HCl that actually was. And that was only 0.05 moles of HCl. So then we take our 2.9 kilojoules divided by that, and that'll give us how much energy per mole of HCl. All right, and the result is our amount of energy released by the per mole of HCl, and that is our delta H, heat energy lost by the HCl in the process. All right, so I'm not going to go through this one. I'll let you guys pause and work on it if you want to. All right, so you can do that now if you want to, and I'll give you a chance to see the information on this slide that talks you through it. Hopefully you had a chance to try it yourself at least once a little bit. Okay, so there's a little bit extra information, right? You need to identify the limiting reactant, right, which is a little bit extra work. Okay, so here's another one. This one is very similar to ones we did before. We have the mass of the sample. We transferred it from boiling water at 99.8 degrees Celsius to 152 grams of water at 22.5 degrees Celsius, and the temperature rose to 24.3 degrees Celsius. And we want to know the specific heat of the solid. Well, the temperature change of the water will be how much energy the solid lost, and from that we can identify the change, or the Q, energy in joules for the solid that it lost, right? And from that we can relate that to the mass of solid that there is. So here we have our mass of water. We have the specific heat of water, and we identify the joules of energy lost by the water. This is also the joules of energy, the joules of energy gained by the water because the water heated up. This is also the joules of energy that was lost by the sample, and from that we can identify joules per gram degrees Celsius. So we need to identify the specific heat by dividing by the grams of material and the change in temperature that the sample underwent, the sample of metal. All right. So this is a little bit of a review here. We know that endothermic processes, the heat is being consumed in a reaction, and exothermic processes, the heat is being released in a reaction. Okay? All right. So now we have to have a little bit of understanding about the term standard state. Standard state is how you would find the state in which you would find a chemical under standard conditions, meaning one atmosphere of pressure, which is kind of like how we have it here in Hawaii, and 25 degrees Celsius, or 298 Kelvin. So how much, or what the state, or what the chemical is like under these conditions is called the standard state of the chemical. We also have what we call delta H of standard states of delta H of formation of specific chemicals. And this is how much energy, delta H, how much heat energy is required to make a certain chemical under standard conditions from the chemicals. Here's my eraser. From the chemicals constituents at room temperature. So we call this the delta H of formation. Let's see if we have some examples. Well, we don't really have some examples there, so let's go back to this. That's called the delta H of formation. So if I have a chemical, let's say it's carbon dioxide, all right, and I want to identify how much energy, heat energy, is required to make this carbon dioxide. Well, I want to know, again, how much energy from its elements. So it's going to be carbon and oxygen gas. These are how you would find the elements at under their standard states. Carbon would be a solid. Oxygen gas would be a gas. You combine those two together and you would make carbon dioxide. Now the delta H, the amount of heat energy required or released in this process, would be the delta H of formation. So we'd have a little F right there for carbon dioxide. So the delta H of formation is the energy associated with forming a compound, and you only form 1 mole of the compound, forming a compound from its elemental constituents. All right, under standard conditions, again, at 25 degrees Celsius and at 1 atmosphere pressure. All right. So here is an example of a standard heat of reaction for a chemical reaction. Here we have nitrogen gas coming together to, let's see, nitrogen gas coming together with hydrogen gas to form ammonia. Now in the reaction, you see that there's N2 and 3H2 come together, and the product is 2 ammonia molecules, 2 molecules of ammonia. All right, and it says here when nitrogen and hydrogen react to form ammonia at 25 degrees Celsius and 1 atmosphere,
92.38 kilojoules of energy is released. All right, so that means the delta H for this chemical reaction is 92.38 kilojoules, and it's a negative 92.38 because it says that this energy is released. So we can write this reaction, and we can state it like follows. N2 gaseous combines with 3H2 gaseous to form 2NH3 gaseous. And then we say our delta H for this reaction is a negative 92.38 kilojoules of energy. So 1 mole of nitrogen gas combines with 3 moles of hydrogen gas to produce 2 moles of ammonia, gaseous ammonia, and the negative sign, and releases 92.38 kilojoules of energy. This process releases that much kilojoules of heat energy. That's what the delta H says. Okay? So, it would be different, as we see from this slide, it would be different if our delta H, if our product was liquid ammonia, for example. We have another example here down below on the bottom of the slide where CH4, methane, combines with oxygen to form carbon dioxide and water. And we have two scenarios, one where liquid water is formed and one where gaseous water is formed. And you see that the one where gaseous water is formed, less energy was released to the surroundings, negative 802, as opposed to when the liquid water was formed, it was more than 802, it was all the way up to negative 890.5 kilojoules of energy. So, why the difference? Well, the difference is because in the bottom one, some of the energy had to go into converting that liquid into a gas. And so there was less heat energy to release to the surroundings. So it's important that when you identify the delta H of reactions, that you take into account the states, solid, liquid, gas, of the element or the reactants or the products, the chemicals in the reaction. All right. So, we saw this chemical reaction just a little bit ago, the nitrogen combining with hydrogen to form ammonia, right? And we saw the delta H associated with it. All right. Now, to be a true delta H of formation reaction, like the very bottom shows there, the delta H